The next example from Limtreboka, which we are going to have a look at, is number 6, which is going to show us a double tapered beam. So you see it on the left hand side, the system of the model. We do have a 20-meter span between the columns, and in the middle of the beam the height is the biggest, while on the supports it is the lowest. So we do have an angle in the top of the beam by 3.6 degrees. But this example is quite interesting because we do have a couple of issues here we need to check. The one is to check in the middle of the beam, where the Eurocode has specific checks we need to do, because in the middle of the section the angle of the compression is going to change, which means that we do have a tension out of the section which needs to be checked if the section is okay. The higher the angle, the more tension we do have across the section. The next thing is that the one part of the beam, either the left or the right hand side, is to be considered as a single tapered beam, and in that case the maximum moment is going to decrease. We see that one a little bit later. You see the section here. The biggest moment is in the middle of the section, but well, this is actually the sigma m, the tensions across the section, and the biggest compression is not in the middle of the section actually, but it could be at a different position. So your calculation program, if it does its jobs, you will have the maximum utilization in a different section of the beam, and not necessarily in the middle of the beam, as we do have the highest section here. So let's just switch to our calculation program, to NODEMaple. I've already opened it, so this is example 6. We do call this one a Saltax breaker, or a double tapered beam. In that case, we do have, I probably forgot that one, we do have 3 different files. The thing is that section 6, we need to check 3 different sections. We need to check the section in the middle of the beam with its specific checks according to the Eurocode. We do have the section, of course, at the supports, where we probably might have a shear problem. And we need also to check the maximum tension or compression of the outer layers of the glulam beam, as I've shown you previously, with the calculations for a single tapered beam. So let's just start in the middle of the beam, the Mona, the biggest section with 1430 millimeters. We do have these strength class, service class, and load duration classes. And the next thing is the buckling length. In that case, it's not really important because we don't have any compression at the beam, while the lateral torsional buckling, of course, is interesting. So we do have around the weak axis, it's no problem, but I'm sorry, across the big axis it's no problem, but across the weak axis we need to define the distance of the compression system. In that case, I think we have done 5 meters, which is somewhere here in the definition. So let's assume we do have a 5 meter like it's shown here. The secondary beams are prohibiting the lateral torsional in that case, as they're going over the whole section. So let's just continue. We do have the 5 meters here. We are going to check the middle section, as I said, so no supports and no compression at angle to the grain. But we do have a member with varying cross section and curved shapes. So in that case we are going to use the double tapered beam, and with an alpha degree of 3.6. The other ones are not so interesting. In that case, we're going to have the moment check with a moment of 11 to 1, and calculation is done automatically, and we are going to check beams subjected to either bending or combined bending and compression. So the result details are shown here, and we also have design of cross-section members with varying cross-section or curved shape. So all the checks here are not gray anymore, but they are going to be checked. We have the 643 with an utilization of 82%. But of course the section is also checked with the lateral torsional buckling, and the highest amount of the checks is going to be used, which is 0.88. How these checks are done is of course defined in the Eurocode, so you have everything here in 0.6, 0.4, 0.3, double tapered, curved and pitched cambered beams. You can check the results by yourself, of course. So let's go back and open the second file, which is in the middle of the section. We do have a single tapered beam. That's that one. The height is 1153 millimeters, and we do have again the 5 meter for the lateral torsional buckling. And we have a single tapered beam now with 3.6 degrees. And important is the tapered size is in the compression zone in that case. So the moment is of course reduced now, and we do have the maximum utilization is 0.98 here, which is also done here. And let's just switch over to the last check, which is a check of the support. We have the least height, 800 millimeters. We don't have any moment anymore. We just have the shear force. Actually, this is not the check of the shear force. Well, we do have both here. We do have the compression perpendicular to the grain again, and we also have the shear check. So the shear check is going to be here. You need to input it as the VYD, and check is done as a shear check here. And if you're going to the support, which is the perpendicular to the grain, -223, we've had that before, compression perpendicular to the grain, and the check is done with the Eurocode, Euro norm 0.88. So that was it for today, and we're going to continue with the next example in the next video.